I want to do one last thing under stationary analysis of when we input random processes through stable linear systems. We're looking at the output. It's still that same module um, where we started with steady state. So this is the last subject under steady state analysis or stationary analysis. Let me turn off my phone. And we want to look at this white noise, pure white noise versus band limited white noise. So we'll take this example of a first order transfer function, a first order system, compare unity white noise, which has this power spectral density, and band limited white noise, which has this power spectrum. It's a value of 1, just like white noise, but only over certain frequencies between plus and minus omega sub c. In this first case, in previous videos, we already calculated the mean square value 3 different ways. It was 1 over 2t, and the bandwidth of that guy was 1 over t. Now let's look at this second case. We can't use those I sub n formulas and do spectral factorization, because if you look at that, you're taking an integral of this power spectral density over infinite frequencies, and this doesn't break up that way. You can't express it as a polynomial over a polynomial, that's c over d, from minus infinity to plus infinity. So we can't use that one of the 3 methods. So we're stuck with the other 2. Let's see what we've got here. So here was our system. Here's the input power spectral density. Here's what, we ultimately want to get to this formula. And the middle part here is that. Going to be that. And this power spectral density on the input was just the 1, but only between certain frequencies. So our output power spectral density looks like this. It's going to be this guy, but only between those critical frequencies. And this is not in your Fourier transform table, so that pretty much eliminates another one of the 3 methods. So we're kind of stuck. We need to take this integral. Here was one of the 3 methods, taking this integral, evaluating this integral, finding the mean square. Take that integral. Taking this guy, but only between those critical frequencies. I'll change it a little bit because this part is going to be in a table of integrals. So we can use the table. This is still kind of a pain in the butt method here. So here's what's in the table. Here's what it means to us. And finally, you get this for the mean square value. It still looks a little squirrely. We want to compare these 2 guys. The mean square value when the input's pure white noise, and the mean square value when the input is that band limited. Well, they look kind of different. But let's look at things a little. Here's the band limited case. I'm going to define this omega sub g as the bandwidth you get with the pure white noise input, so that I have this ratio of frequency. Now I'll look at the limit as this limit gets large, goes to infinity, as basically the bandwidth of the band limited white noise and the bandwidth you get with the pure white noise. And that limit is the same as the white noise. So if that ratio is big enough, you get no error in the mean square value. If the bandwidth of the band limited white noise is much greater than that of the system itself, then you get relatively little mean square error. and you get relatively little error in the mean square value by just approximating the band limited noise as pure white noise. And here's where the ratio, if that ratio is 64 to 1 or greater, the error in the mean square value is less than 1%. That might look big to you, but when you talk in terms of frequencies, you're usually talking powers 10, 100, 1,000, etc. So the 64 to 1 is not all that. It's just 2 orders of magnitude. You have 2 orders of magnitude in bandwidth more than the bandwidth of your system, and you're introducing almost no error. Anyway, that ends stationary analysis. Then we'll look at transient analysis, which means all these characteristics of the output signal over all time, not just in steady state as time goes to infinity. Have some fun doing that.